All right, today we're talking about matter and thermal energy. So let's first talk about the kinetic theory. All right, this is simply an explanation of how particles of gases behave. So if we first take a look at this, we have to have a couple of assumptions. One is that all matter is composed of tiny particles. And two, that these tiny particles are in constant motion. So like the screen that you're looking at right now, it's actually moving. You're like, what? Are you serious? That can't be it. Nope, it's happening. So think of it this way. Let's say I was standing 5 feet from you. Right? And I take a big step to the right. I take a big step back to the left. Did I move? Like, duh, you're right there. I saw you move. Yeah, okay. Now, let's say I am like 15 miles away, right? And we clear all the land. We bulldoze down all the buildings and hills. And so it's a complete clear line of sight to me. Now, when you look at me, am I going to be very big? No, I'm going to be itty bitty. Right? A little black dot. Right? Now I take a big step to the left, a big step back to the right. Did I move? Well, no, that's not going to look like I moved at all. Well, that same thing is happening with these atoms. They are so itty bitty, teeny weeny that we can't see them moving, but they actually are. So these particles are in constant motion. Now, these particles also are colliding with each other and their surroundings. Okay, and when they do this, they're not actually losing any energy. Or if it is, it's really, really small. It's almost like they're not. So we're going to talk about a couple of phases of matter here. You know the big three, right? Solids, liquids, gases. All right, they're going to be talking about one more today. So a gas, what do we know about gases? Well, they have no fixed volume or shape. In other words, I can take all the air in this room and put it into a little bottle. Right, like an aerosol can. And if I have an aerosol can, I can spray everything in that can and it'll go out of that can and it will fill the entire room. Like if I take perfume and somebody takes too much cologne, they spray a little bit too much and it like kills everybody in the room. I should say kills everybody, but yeah, it's like, oh my gosh, who put on too much perfume or cologne? That's exactly what's happening. Gases can fill the whole room. So they have no shape. They have no volume. They fit whatever container they're in. Liquids, on the other hand, they have less energy, okay, they're gas, but they do keep their volume, but they change their shape. In other words, I take a glass of water and I pour it out, it'll hit the table and flatten out, all right? Volume stays the same, but the shape changes. Now, solids, on the other hand, have the same shape and the same volume, right? They don't change unless you break something off. This leads us to something called a crystalline structure. All this means is that the particles have, the atoms are in a geometric pattern, right? A specific pattern that repeats itself. Plasma. Now, plasma is matter that has enough energy to overcome not just the attractive forces between these particles, but also the attractive forces within its atoms. Okay? So what does that mean? Well, let's take a look at this next diagram here. So as we take a look at the top here, as energy is increasing, we first start off with solid particles. So the particles in a solid, they're vibrating next to each other. So I take two fists, I put them next to each other, I kind of rub them back and forth, right? That's a solid. Now a liquid, I add a little bit more energy to it, add a little heat, all right? And those particles now have enough energy where the bonds between the solids are enough to break so that now they can roll past, they can slide past one another, but not enough energy for them to separate. All right, so now a liquid can then fill or change its shape where a solid can't. Now I add even more energy, and now all of a sudden I have enough energy to break those attractive bonds between different atom particles. And so now they're spreading out throughout the container. So a gas has enough energy, those particles have more energy, and can spread throughout the whole gas container. Now, if I add even more energy to that, then we get into something called plasma. Now, plasma is the most similar to a gas phase, okay? But these particles have so much energy that they actually have kind of broken up into positively and negatively charged ions, okay? So, which of these four states do you think is the most common? Hit pause for 2 seconds and then hit play again. If you said Plasma. You are correct. So the most common form of matter or state of matter is in the universe is plasma. This is the plasma actually is stuff that kind of makes up the stars. So, and their stars are pretty big, and there are a lot of them. So plasma is the most common form out there. All right, stepping a little bit here, we're going to talk about thermal energy. Now, thermal energy is total energy of materials in the particle. Okay. We take a look at the definition of temperature. So if we take a look at temperature, we use kinetic energy, all right? And the definition is the average kinetic energy of the particles that make up a substance, right? Kinetic energy is the energy of motion. So we take a look at this graph here off to the right. Which of these lines, the black or the red, represents a higher temperature? Hit pause for 5 seconds, answer it, and then hit play again. Correct answer is the red line. If we take a look here, many people said, oh, the black line's got to be the higher temperature because it's a taller curve. Well, if we take a look, remember, temperature is based on the average particles moving. And here, we have more particles, or the average speed is higher with the red, even though there's less particles moving than the black. So remember, the average speed represents temperature, not how many particles. Temperature conversions are, you can go back and click on this on through the slideshow or use your formula sheet on how to properly convert temperature later. But moving right along, we're going to talk about the melting point. Now, the melting point is the temperature at which a solid becomes a liquid, which leads us to something called the heat of fusion. Now, the heat of fusion is the energy required to change a substance from a solid to a liquid at its melting point. Now, different materials will have different heat of fusion. In other words, it's going to take different energy requirements. For example, you take a look at an block of ice and a metal bar. You put it on a stove. You turn on the heat. Do they melt at the same time? No. Ice melts way sooner than the metal rod because the heat of fusion is different for both of these. Now, there are two types of vaporization. Okay, now vaporization is going from a liquid into a gaseous form. Now, evaporation and boiling point. These are two types of vaporization. Evaporation takes place at the surface of the liquid, where boiling occurs throughout a specific temperature. All right, so think of this way. Looking at this evaporation, like I spill something on the floor, all right? I come back and that water, evaporates. It goes away without any heat. Whereas boiling, I have to add heat to it, and then that temperature changes throughout the whole substance and then gets turned into a air liquid vapor. So the boiling point. This is the temperature at which the pressure of a vapor in the liquid is equal to the external pressure acting on the surface of the liquid. Now, some of you are like, well, boiling point changes from place to place. I go to Colorado versus Florida. Which one do you think has a higher boiling point? If you said Florida, you're right. Well, Colorado has less air pressure, less atmosphere, higher up, right? And therefore there's less atmospheric pressure, and therefore the amount of energy required to break free from a liquid is less. So therefore the temperature to boil water in Colorado is less than that of Florida. Heat of vaporization is the amount of energy required for a liquid at its boiling point to become a gas. And that changes depending upon the type of material that is being vaporized. So if we look at a heating curve, you'll notice that it goes from you got these flat areas here where it rises up, flattens out, rises up, flattens out. Well, why is that? Well, if we look at the amount of energy going into it, all that energy goes into the phase change. Okay, so here you'll notice that it flattens out. Well, when the ice completely melts, when all the energy goes into melting the ice, when all that ice is gone, then the energy goes into heating up the liquid. And then it flattens out again, and this is where all the energy is going and turning the liquid into a gas. And then once all that's into a gas, then the gas temperature starts to increase. So that flat area is all about turning energy and changing the phase of the material. So sublimation. Sublimation now is a little bit different. This is the process where you go from a solid straight into a gas. It skips the liquid phase. An example of this would be ice cube in the freezer. Put ice cube in, come back a couple of months later, that ice cube shrunk. Well, where did it go? Well, sublimation took place. Deposition is changing from a gas going directly into a solid, skipping the liquid phase. Example of this would be frost. Okay, it didn't rain, but there happens to be frozen water on the ground in the morning. Here we have an example of the phase changes. You'll notice here sublimation and deposition, where we're skipping from a solid to a gas and a gas to a solid as deposition here. Going from a solid to a liquid is melting. From liquid to gas is vaporization. From gas to liquid is condensation. And from liquid to freezing is a solid. You'll notice here also that as I go from a solid to liquid to a gas, I'm adding heat. And by adding heat here, I'm changing a couple of things. I'm adding kinetic energy, right? The energy starts to increase. The particle speed also increases, right? So the heat increases, energy increases, speed increases. But as I go up, something happens. Those particles start to spread apart, like in a gas, right? The gaseous phase. And therefore, the density actually decreases as I go from a solid to a liquid to a gas. You'll notice here the boiling point, this flat line here, this is where, depending upon if I'm adding energy or taking energy away, one of two things will happen. If I add energy, I'm going to turn it into a gas because I'm boiling, and condensation will take place if I'm taking energy away. Same thing down here with the melting point. If I add energy, I'm melting it, turning it into a liquid. I take energy away, I'm freezing it, turning it back into a solid. So energy being added is melting and vaporization, and energy lost is condensation and freezing. Now, thermal expansion. What is thermal expansion? This is when I increase the size of the substance when the temperature is increased. So like in a highway, right, the concrete buckles, right? Particles start to move faster as I add heat, right? And so the concrete has to go somewhere. It can't go down into the earth. The only place it can go is up. And so therefore the concrete buckles and it breaks up. Not everything expands with heat, okay? Some things expand actually going the other way. And that's, for example, is water. Water will actually does the opposite. Actually, it expands when it gets turned into the solid form, because here we have water molecules here all kind of mixed together, and when it freezes, it forms a crystalline structure. And that crystalline structure, remember, it's that repeating form of atoms. These atoms then expand, all right? There's more space, so that's why ice floats on water, because it's less dense, because it's expanded, because of that structure, the crystalline structure. Last but not least, we have something called an amorphous solid. This simply lacks a crystalline structure. Okay, so we know a crystalline, the atoms are put together up in the right-hand corner here. The atoms are all in nice arrangement. Amorphous simply means that it lacks that structure. Everything's kind of thrown together and mixed up. So that's lecture for today. Good luck.